All right, here we go. Welcome to physics. It is October 29th or 30th, depending on when you're watching this. Uh, Today what we're doing is graphing. I know a lot of people have been super excited about this and saying, Mr. Reimer, graphing was my favorite part of grade 10 physics. That's why I took grade 11 physics. When are we going to do graphing? Well, I've heard your cries and your pleas for more graphs. And so I've made this booklet. And if it's in your hands, you've thought to yourself already, of all the lessons that are 10 pages long, I'm so happy it's graphs. I'm so excited for what we're going to learn. This must be really good because it's 10 pages. I'm with you. It's going to be a blast. I'm excited. Graphing is great because numbers only tell you so much. And you have to do a lot of assuming, whereas graphs, they show you a picture. It's like art with math. What's better than that? Nothing. That's what. And so let's start graphing. Where we're going to begin is with a simple example. A plane is moving away from the airport with a uniform. Uniform just means unchanging, like, hey, we're all the same. It's always the same, right? If we're all in uniforms, which would be simpler, quite honestly, then we would all be looking the same, and a velocity that is uniform is always acting the same and moving the same. So it's a constant 3 meters per second north. Notice this is north, and so up is north. That's what that means. So we're going to plot this motion on the graph. Let's start at the origin. Remember, this is the origin. Let's start there. And we're going 3 meters every second. Okay, this is not going to be a very exciting graph because after 1 second, we are at 3 meters. That will be right there. So we put a point there. And then after 2 seconds, it'll be 3 more meters. So it'll be at 6. After 3 seconds, 3 more. We're at 9, and so on. And then you take a ruler and you connect the dots, just like that. There you go. There is the graph of this motion. I should have used a different scale, but I didn't. And as soon as I started drawing it, I thought, wow, last time I did this question a year ago, I thought I should have used a different scale. That's unfortunate. After 0 seconds, we had moved 0 meters. Why are we doing this? This is called a table of values. You should have seen this in math multiple times already. And if you haven't, I'm pretty sure you have not been listening. Table of values. After 1 second, we will have moved 3 meters. After 2 seconds, we will have moved 6 meters, and after 3 seconds, 9 meters, because we are moving 3 meters every second. And so after 1 second, 3 meters, 3 more. All right, so we need to be able to get something like this, and hopefully you can see how a table of values is related to this graph. We plotted 0, 0. These 2 points, these 2 numbers create a point on a graph. These 2 numbers create a point. 1 for the time. Notice how time is labeled in seconds on the bottom, and the displacement is labeled in meters on the side. And so 1 second correlates with 3 meters, and that creates a point on the graph. Hopefully that is familiar, and this is relatively review-ish. Let's calculate the slope of the line. You would have learned this in grade 10 pre-cal, and so let's figure out what slope is. To find slope, we do rise over run. You can pick any 2 points. And if it's a straight line, it won't matter. So let's pick these 2 points. Okay, right there. The rise here is 3 meters. Notice how the rise is in meters because it's going up and down, just like the displacement on the side. And the run here is 1 second. Oh my goodness. I think I see what's going to happen already. We're going to get the rise over the run being our velocity. And in fact, that's always the case. Rise over the run, in this case, would be 3 meters in 1 second. And that gives us 3 meters per second. Isn't that cool? We learned this last year. The slope of a graph, the slope of a line, represents the speed. Okay? Slope of the line is the speed on a graph. So the question is, how are the velocity and the slope of the line on the position time graph related? They are the same. Very good. Boy, didn't you miss this stuff? Example number 2. A cyclist maintains a constant velocity of 5 meters per second. At time 0, 0, the cyclist is 250 meters from point A. Well, look at this. It's already shown. At 250 times 0, 0, the cyclist is there. What's the cyclist's position from point A at time 60 seconds? Well, he started off 250 meters from it. And at 60 seconds, he is 550 meters away from point A. Okay? Maybe away, I guess. Okay, so how do we get that? Is we looked at 60 seconds and we found the line. The line was traveling here, so we found where the line that we care about, green line now, intersects with 60 seconds, and that's right here. And we think, well, what's the cyclist's position? The position is demonstrated or displayed on the left side, on the side of the graph. So time is on the bottom, and what's the corresponding position? And that would be over here, 550, and the units would be meters. What is the displacement from the starting position to 60 seconds? Okay, well, he's 550 meters away from something, from point A, but his displacement over the 60 seconds was this distance, right? He started 250, now he's 550. So his displacement would be 550 minus 250. If you get your calculator out, you probably need it for this one. You get a total of 300, two sig figs, right? 300 meters is his displacement. Okay, displacement is how much it changed. Let's do another question. Example 3. Below is a position time graph for Josie and Heike paddling canoes in a local river. Wow. Okay, we can figure this out. At what time are Josie and Heike in the same place? Well, we don't even know which is which, but we can figure it out. But when were they, it doesn't matter who is who, when were they at the same place? Right here. And that is at time 6 minutes. Okay, 6 minutes. So you cannot just decide it's seconds because you like that. Oh, but it says seconds. Come on. How do we get from minutes to seconds? We multiply by 60. So it's at 360 seconds. What a great question. How much time does Josie spend on the river before he passes Heike? Well, who is Josie and who is Heike? Well, just the fact that we know that Josie passes Heike. Which one's Josie? This one has to be Josie because this is the line that passes this one, which must be Heike. Or Hike. I don't know what his name is. All right. How much time does he spend on the river? Well, you're tempted to say, oh, it's 360 seconds. Hold on a little bit here. He only jumps in the river there, right? And this is at precisely 0.75 minutes, okay, which is, or 45 seconds, right? 3/4 of a minute. And so we got to take away 45 seconds. So 360 minus 45 is 315 seconds. So how much time does he spend on the river? The answer is 315 seconds. Do we need a direction? No, because it's in time, and we weren't given. Oh, it is north. Where on the river does it appear that there might be a swift current? Tempting thing to do here is say, well, it happens twice. It happens here between 2 and 3, right? You can see hiking just often speeds up. And then it happens again at 4.5 and 5.5 and 5 seconds, right? But wait a minute, those are times. We're not looking for times. We got the right spot, but this is at a location between 4 and 5 decameters past the origin. Okay, so the answer would be between 4 and 5 decameters north of wherever the origin is. Okay, so that's the answer. As you can see, if we look down this line, we see that both Heike, and so what you can see is there are, if you look down this line, this is the time, the place, it's not the time, it's the place where both Heike and Josie sped up quite a bit. And how do we know they sped up? Because the lines are more steep. I don't know what I was saying, keep getting interrupted here, but hopefully you get it. What's the instantaneous velocity? Oh yeah, I was saying something about steeper the line, the more faster going, right? Josie's covering more distance than Heike every second. Okay, that's why it's more steep. So what's the instantaneous velocity at 8 seconds of both riders? So we're looking at this time, but remember that at any point in the line represents, like this, if it's a straight line, the slope doesn't change. And so what I'm going to do is I'm going to take 2 points. Here's a point, and here's a point, and there's a point, right? And so for this line, we take the rise over the run. The rise here is 2 decameters, and the run is 2 minutes. And so this is Josie. So maybe the way I'll write it is this: the velocity of Josie is, so Vj is the rise over the run, right? So he traveled 2 decameters in 2 minutes. And so that is 1 decameter per minute. That's a velocity. It's a pretty trashy one, but whatever. That's a 1, by the way. Okay, Heike's, the velocity of Heike is going to be at 8 seconds. We just need to find the slope on this line. Well, he did 1 decameter in 3 minutes. So 1 decameter in 3 minutes, which is 0.33 decameters per minute. There you go. Good enough. We found the speed based on the line. How do we find acceleration based on a PT graph? This is for position time graph. Okay, that's what PT graph stands for. It could be sometimes it's DT for like displacement time. They're the same thing. All right. If the line is flat, the object is at rest. If the line is going up like this, it's a positive velocity. Going down, this is a negative velocity. If it's flat, it's 0 velocity, right? These are the same. They're at rest. If we're curving, that's when we have a positive acceleration. Okay. Another example of this would be a negative acceleration if it was like this, right? Because we are getting faster, but in the negative direction. We're speeding up. So this is speeding up in the negative direction. Okay, in negative direction. This is negative acceleration. This is slowing down, but in the positive direction. You know what I mean by that? Good. It means you're still moving up, right? You're still moving positively, but you're slowing down. And so this is a negative acceleration. Okay. This is also a negative acceleration. Okay. This is a positive acceleration, but in the negative direction. Okay. See what this looks like? We're moving down, but we are slowing down, which means we're accelerating in the positive direction, but we're moving in the negative direction. So negative direction, positive acceleration. Weird stuff, eh? But notice how acceleration is always curvy. And so let's do some. We did something with last year with instantaneous velocity. We found it by drawing a tangent line at the exact time you want to know the velocity. So once you have a tangent line drawn, you can calculate the slope. Remember how the slope represents the speed or the velocity? To find the velocity at that exact time. So at 2 seconds, what we do is we put a dot there, and then we use a ruler to draw a very straight line that touches. So that's a terrible line. Try again. That's went through it. It's got to be, that's close. You should use a ruler. I didn't. But you need to. And then you get 2 nice points. So like, oh man, it's not perfect, but this is a nice point. That's right on. And let's just say this was right on. It's pretty close. And so then you find the slope of that line. We went over 4 seconds and we went up. That looks like 3 meters. So the slope is 3 meters in 4 seconds. And you should get something like 0.75 meters per second. So if you do it yourself with a ruler at 2 seconds, you might get something slightly different, but it will be close. We'll get something close to 0.75. It's amazing how close everyone gets if they do it. What I don't want to see is I don't want to see lines going through both of them, and I don't want to see it for sure like that. That's both terrible, okay? It's got to be something similar to that. Mine, I might critique it a bit because you can see it goes on the wrong side of this black right there, right? That's not good. And so there is definitely critiques of mine. You should use a ruler. You need a ruler for this. If you don't use a ruler, it's garbage, like mine line. Average velocity is found by drawing a straight line from the beginning to the end of a time interval and calculating the slope of the line. That's how we find the average velocity, because we don't care, for average, we don't care about the path that we took to get there. So if we've got a graph and we want to calculate the average velocity between 0 and 4 seconds, okay, well, 4 seconds, we were here, right? And where do we start? Here. Well, we were going no speed and then really fast and then no speed again. But none of those are our average velocity. Those are where there's 3 different velocities that exist here. But if we want our average velocity, what we do is we draw a straight line. Okay, and we find the slope. So the slope of that line is the rise, which is it went up 40. And the run is it went over 4 seconds. 40 meters in 4 seconds, right? And so what we get is the slope is 40 meters in 4 seconds. That gives us 10 meters per second is our average velocity. Okay, and that's positive. That's the direction in this case. From 0 to 6 seconds, do this in red. Well, at 6 seconds, we are here. What's the slope of the line? Well, we want a total rise. The slope here, 0 meters is a rise over 6 seconds, gives us 0 meters per second. All right, and so, yeah, I know that we had a speed and then we had another speed, but overall, we went nowhere, so our average velocity was 0. Velocity cares about direction. So on a graph, we can figure that out, all right, from 0 to 6 seconds. Our average speed was 0. We do. If we wanted to find out what our average velocity was between 4.5 seconds and 6, we could, right? But that's not the question here. And we're not doing this for fun. I mean, we are doing this for fun, but there's a lot more to do, so we're going to keep going. Example number 6. A car is driving down the highway with a velocity of 100 kilometers per hour north. Oh, nice. It's in kilometers per hour, so this is pretty sweet. All right, next question. Now, I guess we should probably do something with this. I just wanted to show you how to set up a graph, okay? If we're going to set up a nice graph, we're going to make 0 the origin, and I really should have put more examples here about instructions, I mean. But, oh, this turns in seconds? Kilometers per hour. Oh, that's why. I know what's going on here. Sorry. I wish I could cut this out of the video, but I don't know how to. So that's embarrassing. This is a moment of me not being prepared for the video I'm making, but I know what's going on. This is a velocity time graph. It took me so long to figure this out. How do you draw a velocity time graph? Here's how. I'll show you. Let's set this up so that we just go up 3, 4, 5, 6, 7, 8, 9, 10. Okay, after 10 seconds, what's going to happen if we're going 100 kilometers an hour? Well, this is a velocity time graph. So let's go up by like, I don't know, 20s, 20, 40, 60, 80, 100, 110, 120, 140, 160, 180, 200. Okay, so we start off at the origin. No, we start off with a velocity of 100 kilometers an hour. Well, what are we measuring? We're measuring velocity versus time. And so where on the velocity line, on this y-axis, would 100 kilometers an hour be? Well, it'd be right here, because this is kilometers per hour. This dot represents that at time 0, we're going 100 kilometers an hour. Well, how fast are we going after 1 second? Well, it says we're driving at 100 kilometers an hour, so it doesn't imply that we're changing speeds. And so if we're here, we're still going, well, 100 what? 100 kilometers an hour. Well, after 2 seconds, we should still be going the same speed. And so if we're here, we're going 100 kilometers an hour. So what we're going to find is Mr. Feast just won the Tim's card. You guys didn't get it here. But today they're having this draw. I don't know if you noticed. Oh, you're probably in school right now. That just pisses me off. That guy doesn't deserve anything. He better give it to me. All the amount of time that I help him with tech stuff, can't get his projector to work. And it's, oh, Mr. Reimer, come and help me. He better give that Tim's card to me. Anyways, what we're going to get here is a straight line all the way across. And so what does a straight line mean? This means that for all 10 seconds, we are going 100, not meters, but kilometers per hour. So this is now a speed graph. A straight line here represents 100 kilometers an hour. Yeah? Isn't that cool? So on a velocity time graph, uniform velocity is represented by a horizontal. Horizontal means flat line on a VT graph. Okay, on a VT graph. Notice that now we've got two types of graphs. We got velocity time graph and we've got position time graphs. Okay, and there's a big difference. So now we always have to check what type of graph are we working with. This is the velocity time graph because it says velocity on it. All right, and so let's look at example 7. A car is driving down the highway with a velocity of 100 kilometers an hour north for 4 seconds, then it stops for 2 seconds, then drives at a speed of 100 kilometers an hour south for the next 4 seconds. This is neat. Okay, so draw a straight line down the middle because we're going to go on both sides of this line. This is kilometers an hour. Let's make sure we specify that this is north. Okay, so positive is north. And let's go 25, 50, 75, 100 kilometers an hour north. It's kilometers an hour. And minus 25, minus 50, minus 75, minus 100 kilometers an hour. So that would be south because negative north is south. And our time is just going to be pretty straightforward. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Very good. Now, how do we graph this? A car is driving with a velocity of 100 kilometers an hour north. Well, that's right here, right? For 4 seconds. That's all the way till here. And if it had a steady velocity, it's just a straight line at 100 kilometers an hour. It then stops for 2 seconds. Velocity, this is an instantaneous stop, which means he died. And then 2 seconds of that stop, and then immediately is going 100 kilometers. Oops, missed that line. Then immediately is going 100 kilometers an hour south. That's this way. So you hit a brick wall and then got picked up by a different and roll onto the road. In 2 seconds, and got hit by another truck to go 100 kilometers an hour the other way, right? This is a very violent scene here. It doesn't look bad, but this is extremely violent. Having this much acceleration, that's deadly. So anyways, that's how we plot it, okay? All we care about is speed when we're doing a speed graph or a velocity time graph, okay? On a velocity time graph, an object at rest, where was this car resting? Right here, okay? This kind of looks like resting, but if you know that you're plotting velocity, you know this guy is far from resting. He's moving 100 kilometers an hour. This is resting because his speed is 0, okay? So objects at rest are represented by a line along the x-axis on a VT graph. Okay, this is called the x-axis, right? In math, you always do x, and up and down is y. That's how you always do it. And so anything along the x-axis, that's at rest. Okay, so let's do one more example here. A Tesla is driving down the highway with a velocity of 100 kilometers an hour. Let's set this up. This is very similar, okay? Let's draw a nice straight line here. This is time. I think we can do, say 1, 2, 3 for time. Velocities, let's go again. I think that if we do this, we got 0, 25, 50, 75, and 100. And let's go negatives in the other direction. All right. A Tesla is driving on the highway with a velocity of 100 kilometers an hour north for 2 seconds. Well, we got to make this north. It then spots a deer and slows to a stop in 2 seconds. Okay, so let's draw this. Starting here at 100 kilometers an hour, he's going 100 kilometers an hour for 2 seconds, and then slows to a stop in 2 more seconds. 2 more seconds later, he's going to be stopped. That means his speed is 0. Remember, we're plotting speed, and so he has to slow down in 2 seconds. There you go. He then decides, he then rests for 2 seconds. Okay, so this line's going there. Maybe I should be using purple for this. Okay, so we started here, line across, slow to a stop, stops, and after 2 seconds, he decides the road is too dangerous, accelerates to a speed up to 100 kilometers an hour in 3 seconds, and then drives away. Okay, and so we got 1, 2, 3 seconds later, he is the opposite direction, going 100 kilometers an hour. That's there, and then speeds away at 100 kilometers an hour. Okay, so we're just plotting speeds here. We're not plotting distances because this is a velocity time graph. And this is south because it's opposite of north. And so I want to highlight here, acceleration is represented by a not horizontal line, but a sloped line. On a VT graph. We're used to acceleration being a curved line, and that is up here. Remember here we saw a curved line. We just wrote acceleration is a curved line, but this is just, this curved line nonsense is just position time graphs. So we've got 2 different graphs that we're going to be working with over the next couple of days, and that is going to be the velocity time graph and a distance or position time graph. Now, how can you tell the difference? They look so similar. There's one difference, and only one before they're set up, and that is it says it. So, can you read? Yes, you can. Have confidence. You can read. And since you can read, you should. And you should definitely read what you're measuring. You're measuring speed, and plot the speed. All right, if you're speed and time, continue the time. If you're measuring position, if it says position over here, then plot position. Okay, and that's what you look for. When we made this, we just looked for the speed and we did it accordingly. That's today's lesson. Bring your notes to class tomorrow, and we'll continue on this exciting journey through these notes as we are going to start to compare. If we are given, how do we do displacement? How do we connect displacement and velocity time graphs? Because we have not talked about that yet, and that is quite a rush. That is pretty exciting to learn. So, looking forward to that.